Your typical pump sizing problem would be similar to this. There's a borehole supplying 5 liters per second, a water tank, and 2 kilometers of 160 millimeter HDPE pipe. First, the pump needs to overcome the geometric head, the difference in elevation between the surface of the water in one point and in the other. There's no need to keep the usual 10 meters pressure safety margin in this case. If we mess up, the pump can compensate. If you're pumping into a system that is already pressurized, you will add the equivalent meters of pressure. For example, 22 meters for 2.2 bars. But in this case, there's no pressure at the delivery point. Second, it needs to accelerate the water from still to the velocity in the pipe. Velocities in water supply applications are usually very low, so we can disregard it. And third, we take into account the energy that will be lost by friction inside the pipes. We look in the head loss tables. We enter a flow of 5 liters per second in the middle column and read the other two. In this case, we fall between 0.8 and 0.9 meters per kilometer, so we take 0.85 for the head loss J. The speed in the pipe is 0.32 meters per second. For 2 kilometers, we lose 1.7 meters. We add them up and we find that the total head for the pump is 85 meters. Now, if you just wanted to double check, you can crunch the numbers and you will see that the velocity just produces a very small head. But let's backtrack for a minute. If we conceive the pump sizing exercise as we've just done, we leave a lot on the table. This problem statement is a logical trap. It leads to inside-the-box thinking. While it is the final tool for choosing the pump sizing problem is much larger than that, with lots of opportunities to reap efficiencies and to screw up. In the next few minutes, we'll go over the process in more detail to understand it better. The first thing you need to know is that pipes, pumps, and water tanks are sized together. We want to find the sweet spot where resources are used efficiently. Even when you have an existing system, look beyond the pump. Is the pipe strangled? If I solarize a system, how much do I have to increase the tank? Bigger pumps mean bigger pipes to accommodate the flow. They also mean smaller water tanks, as water pumped and consumed at the same time doesn't need storage. The opposite is also true. Smaller pumps lead to smaller pipes and bigger water tanks. One huge consideration is pumping costs. Considering the total life cycle, pumping costs dwarf investments in pumps, water tanks, and maybe even pipes. You should always try to cut down the pumping head by lowering the tanks as much as practical. In the case we have just calculated, if you lower the head by just 6 meters, you would get $500,000 in return. There are two main parameters that you can tweak with in a pumping system: the flow and the head or height. They define the working point of the pump. Even if you're using a computer program or a web-based service to size your pump, you will still need to come with them beforehand. It is by affecting these two parameters that we gain leverage over our pumping system to make it more efficient. Once defined, you or the program will choose the pump with the best efficiency among all the ones that work in that working point. Let's start with the flow. The flow influences the head by either affecting the friction in pipes or the drawdown in boreholes. When dealing with boreholes, it is very important to minimize the drawdown by pumping very slowly. Beware of easy 3-point pumping curves. The curve that joins 3 points is the circle we often see in pumping tests, but the reality is not that simple. Pumping curves frequently have inflection points. Take a look at how pumping twice the yield in this case makes the drawdown head 10 times bigger for all the water. It may be more economical to drill a second borehole. Headwise, we start with a heads up. Imagine for a second a bag drifting inside water. As long as it is within the water, it is weightless. It's only when you start pulling it out of the water that you feel the weight. Similarly, the pump may be very deep in the water, but it will only feel the weight when it starts pumping out of the water. So we only care about where is the water surface and not the pump. To sum up, we have the geometric head measured between surfaces. The friction head that depends on the pipe diameter. The smaller the diameter of the pipe, the bigger the head losses and the more pumping energy we lose as heat. And finally, the velocity. One very common mistake is to match the pumping main diameter with the pump's outlet. Both borehole and dry pumps have size restrictions. The outlet diameters of pumps are usually too small. We need to increase it right after the valves that follow the pump. And how about the usual 10-meter safety pressure margin in water supply schemes? We don't need it. The pump can move its operation point to compensate for any errors or unpredicted circumstances. The flow will be slightly less, but we can easily pump a little bit longer. Another thing is that the different elements of a water scheme have different lifespans. While the pipes may be planned for 30 years or more, the pump will certainly not last so long. The pumps will grow in size as they are replaced. There's no need to buy the final pump at the beginning. Sometimes you run into a 3-wire pump, frequently brand new, and either it doesn't pump or there's very little pressure. Before you run to blame yourself or someone else for their poor sizing, or you rush to buy a new pump, take 10 minutes to check that 2 cables have not been swapped around. If the order 123 is changed to 132, the pump rotates in the other direction, and while it is still able to pump, it loses a lot of power. It is very easy to have a misconnected pump and think it is defective. So there you have it. Lots of information in this video. Here's a little recap.